This lesson introduces numerical integration, so you'll find out what it is and why we need it sometimes. You'll also start to focus on one of the methods required for A-level and find out that integration is indeed a limit of a sum. You already know a lot about integration. You have found out how to integrate functions with x to any power, how to integrate e to the something x. You've learned that integration can be represented as an area between a graph and the x-axis. You know that differentiation is the inverse of integration. In year 13, you're going to learn a lot of techniques for doing all sorts of different integrations. But there are some expressions that you can never learn any techniques to integrate algebraically. And this is one example, e to the negative x squared. So we can never find the exact value of the definite integral from 0 to 1 of e to the minus x squared, which is a bit annoying. Luckily, we have got different techniques for dealing with this situation. You've learned an algebraic technique which helps, so that using a binomial expansion to represent a function, that only works when you can write the function as brackets, but it does help. For everything else, we can use a numerical approximation, and we can choose how accurate we would like our approximation to be. So that really almost solves the problem. It means we don't get very pretty answers, but we can get as accurate as we would like. This technique of using numerical approximation is called numerical integration. So we can integrate things, but with numbers. It's only possible to do this if you're finding a definite integral. That's one with limits. Right, so how come it works? If you remember from year 12 that you can represent an integral as an area between the curve of the function and the x-axis. So here's one example. So we're going to look at two different approaches, and the approach we're going to do in this lesson and the next is to pretend we've got a whole load of rectangles that we're adding up instead of a lovely curve. And the next one is to use the trapezium rule, where instead of having rectangles we have trapezia, which look a little bit better than rectangles. Let's see how numerical integration works with rectangles. So we'll use our example of e to the minus x squared going from 0 to 1. We can see the graph of it here. We could get an underestimate of this using a rectangle or an overestimate using a rectangle. So there's our underestimate and there's our overestimate. You can see that the width of the rectangle is the width of the region we want to integrate over, and the height of the rectangle for the smaller one is the height of the graph at that right hand side, okay, because that's the lowest point where the rectangle meets the graph. For the upper bound, it's the same width, but looking at the height, we want the highest point on the graph here, where the rectangle meets the graph. So that means that if we can find out the area of the small rectangle, that gives us an underestimate for our integral that we want, and if we can find the value of the larger rectangle, that gives us an overestimate, a lower bound and an upper bound for the integral that we want. So how do we work out these numbers? We know how to find the area of a rectangle, just base times the height. So we are doing the base, which is just 1, times the height, which is the y coordinate for the right hand side of the rectangle, for the x being 1. And we know the function for that graph, it's e to the minus x squared, so we're doing e to the negative 1 squared. If we look at the other one, we can see the base is 1, and the height this time is the y coordinate of e to the minus x squared, where x is 0 this time, the left hand side. So we pop 0 in there and we get 1 out. Okay, we call the smaller one a lower bound or underestimate, and we call the larger one an upper bound or an overestimate. If we want to be precise and particular, then we ought to round the lower estimate down to make sure it definitely is less than the true value, and we ought to round the upper bound upwards if necessary, if it's not an exact value as it is here, in order to make sure the upper bound is definitely larger than the true value. However, most of the exam questions in the mark schemes, they don't seem to fuss about this, so don't get too worried about it. The last example gave us a rather wide range of values within which our true integral will lie. To get a more accurate idea of our true value, we would want to use more narrower rectangles. To see how this works, we'll start with just two rectangles. So here we have two rectangles lying just beneath the curve to give us our lower bound. If we add up those two areas, it's going to give us a better idea than just the one big wide rectangle we had before. Similarly, if we have two rectangles, this time lying just above the curve, that's going to give us a better idea than that one really wide rectangle that we had before. We know that we should get a tighter range of values this time, and indeed we do. Let's see how we calculate those values. So for the lower bound, we have two rectangles. We're going to have to find the area of each and add them up. This time, when we look at the base, we've got this base times the height plus this base times another height. We could take, because we're going to split it into two equal width rectangles, we'll have the same base for each rectangle. So we could take that base out as a factor here. So now we need to find the two heights. And again, they're taken from the value on the graph. So we look at where the rectangle touches the curve. And we want to look at what the x value is there. So it's going to be 0.5 halfway along. And we substitute that in to our y equals e to the minus x squared. That gives us the height for the first rectangle. For the second rectangle, again, it's at the top right corner that it touches the graph. So we look at the x value is 1. We want to find the y coordinate when x is 1, and we use the formula again. So when we add those heights up and multiply by the base width, we end up with our value for the total area of those rectangles. We do an equivalent thing when we're finding the overestimate or the upper bound. So it's exactly the same as before. We do base times height for each rectangle and add them up. Now, because we've split them into equal width rectangles, the bases are all the same, so we can take base out as a common factor. So we just need the two heights to add up. The height of the first rectangle is taken from where the rectangle coincides with the graph, and we can see it's at the left hand side where x is 0. So we substitute 0 into e to the minus x squared. For the height of the second rectangle, again, it's at the left hand side of the rectangle where it touches the graph. We want that y coordinate, so the x value is 0.5, and we substitute into e to the minus x squared. And that gives us our height. So we add up the two heights times by the base width, and we end up with the total area of those two rectangles. Now, for this graph, for the lower bound, we're looking at the right-hand side of the rectangles, and for this graph, for the upper bound, we're looking at the left-hand side of the rectangles. But you need to sketch the graphs in order to find out which side of the rectangle you need to be looking at, and that helps you write down your expression for the total area of the sum of the rectangles. So there we have it, a lower bound and an upper bound. If we're being fussy, then we would round the lower bound down and round the upper bound up. We're going to get an even better idea of the value of the integral if we split in the area into 5 rectangles. So here's our lower bound, split into 5 rectangles, with little rectangles just underneath the curve. And here we have rectangles just above the curve for our upper bound. what are we going to get this time? How are we going to calculate our values? So we look at the width, the range of x values over which we're splitting our rectangles. So we're going from 0 to 1. We're going to do 5 rectangles. So we do 1 divided by 5, which is 0.2 for our base width. To get our heights here, we are looking at where the rectangle touches the curve. And for our lower bound, every time it's the right-hand side of the rectangle that touches the curve. So we want to know the x-coordinates for the right-hand side of each rectangle, and we're going to substitute that into y equals e to the minus x squared to get our heights of rectangles. So here we go. Let's just remind ourselves. We're doing base times height for every rectangle and add it up. Because the base is the same 0.2 for all of the rectangles, we can take that out as a common factor, and we just need to worry about the heights. The heights are the y-coordinates from the graph where the x-coordinates in this example are the right-hand side of the rectangle. So we've got 0.2, 0.4, 0.6, 0.8 and 1. If we add all those up, times by 0.2, then we're going to get around about 0.681. It's the same story for the upper bound. So we have split the full range from 0 to 1 over 5 rectangles, so the base width of every rectangle will be 0.2. The heights this time are the y-coordinates of the curve for the left-hand side of each rectangle. So we look at the x values, the left-hand side of each rectangle. So that's going to this time start at 0, go up in 0.2s until we get to 0.8. So here we are, base times height for every rectangle. We can take the base out as a common factor and add up the heights. Base is 0.2 and the heights are the y-ordinates where the x-coordinates are taken from the left-hand side of each rectangle. And that gives us 0.808. We have to check if we use from our graph which values we want for our x-coordinates in order to substitute in to find the y-coordinates. If we're being careful, we ought to round our value for the lower bound downwards and our value for the upper bound upwards, which is being done here. Already we can see the effect of having more narrower rectangles, and it gives us a much better view of the actual value of the integral of e to the minus x squared from 0 to 1. For our first one, we had one rectangle and we had quite a wide range of about 0.6. When we had two rectangles, the range is narrowed to about 0.3. And with 5 rectangles, it's less than 0.15. So it's getting better each time. You can imagine what happens if we continue this. Here we can see the effect of increasing the number of rectangles for our integral. So we started with just one, and if we increase that, we can see that we get more and more narrow rectangles. Okay, and we keep going, we keep going. You can increase it as many times as you like, and as you do that, the values for the lower bound and the upper bound get much closer together. And when you're looking at the graph, it's quite hard to distinguish between the rectangles and the curve. You can see tiny little steps there, but it's a really accurate view of the area you're interested in. And in fact, if we continued this further and further and further, we'd end up with a value that always rounds to 0.7468. And with 100 rectangles, we're pretty close to that already. We can see that the range of values within which the integral lies is shrinking all of the time. It's getting narrower. That means that if we've decided to have a particular degree of accuracy for our integral, we just need to increase the number of rectangles until we reach that degree of accuracy. And every time, each rectangle will get narrower. If we continue this process to the limit, so that means we are letting the number of rectangles increase up to infinity and the width of the rectangles decrease down towards 0, that would mean that our gap between the lower and upper bound would also decrease towards 0. There would be an infinitesimally narrow gap, which is basically 0 gap, and we would have found the integral. So that tells us that a definite integral is the limit of a sum of rectangles. You don't need to worry about this too much, you're just meant to understand the basic idea. The things you'll be asked to do on this topic are to use rectangles to estimate an integral, and to use rectangles to find an upper bound and a lower bound for a definite integral. On the next few pages are some questions for you to check your understanding of how to calculate the total sum of the rectangles. So you just need to think about which expression is the correct one, and I will be showing you a hint and then revealing the answers. So you may need to pause the video at appropriate moments for you to have a go at the question. Here's the hint. Here are the answers. Here's the hint. Here's the answers. Here's the hint. Here's the answers. Here's the hint. Here's the answer. 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 So hopefully you realise the massive importance of doing a little sketch and drawing your rectangles on. Next time you're going to learn how to do this all on your calculator very efficiently.